All right, we start.
Good evening, everyone. This is a group presentation by Group 3. We are going to be presenting the topic linear systems. So,
Yeah, can you speak louder, please? Can you speak a bit louder?
okay, sir. Good evening, everyone. This is a group presentation by Group 3 for CSC 707. We are going to be talking about linear systems. So here are my group members. Then I will be starting with Gaussian elimination. Gaussian elimination, it's a very, very important method for solving systems of linear equation, and it's also known as row echelon form, REF.
Yeah, hello. Are you speaking so far? You're using headset? I think I can't hear you clearly enough. You speak louder.
Sorry. Good afternoon, everyone. Can you hear me very well now, sir?
It's a bit better.
Okay, sir. My name is Abdulrahman. We are going to be presenting linear system of equation for Group 3. So I'll be starting with Gaussian elimination. Gaussian elimination, it's a very important algorithm for solving systems of linear equations. It is also known as row echelon form, REF. It's calculated using an augmented matrix format. I'll be explaining what that means as I go on. What is the objective of this Gaussian elimination? If we look at the images on the screen, you will see that there are two images. If you look at the first image, where there's a red line, there's a red line on the diagonal numbers. The goal of this method is to make all the numbers on the diagonal line, to make everything to be 1, as we can see in the second diagram beside it. And the numbers that are below the diagonal line, everything has to be 0. So that is the goal and the objective of Gaussian elimination. Also, if we look at this, okay, I'll be seeing later. So I want to use an example to explain what Gaussian elimination actually means. Here, the first image here, I said we want to solve this equation using the Gaussian elimination method. If you look at the equation on the screen, you see something like x plus y minus z is equal to 9 in the first row. The second row, y plus 3x is equal to 3. Then the third row, minus x minus 2x is equal to 2. So before I continue, I want to say something about this.
Hello, sir. I think that is 2x, z, not x again. That's minus x minus 2z, not x.
Okay, yes, sir. Yes, sir. So minus x minus 2z is equal to 2. So if you look at this this linear equation here, you will see that the first row has 3 columns: the x column, the y column, and the z column. Actually, everything is supposed to have the 3 columns, but as you can see, some are equal to 0. In the first row, the column, in the first row, x, so there's x column, there's y column, and the z column, and the number after it is 9. Same thing goes for the second row and the third row. So here, so the first step in solving this equation, in solving it using the Gaussian method, is to represent the equation in an augmented matrix format. What this simply means is that we take the coefficients of every number in the equation that we want to solve, and we represent it by taking out the coefficients in the matrix format. So here, the first row has x plus y minus z. So the x there has 1 coefficient, the y has 1 coefficient, z has minus 1 coefficient, and there's the 9, which is a constant. The second row.
Hello, sir.
Sir?
Yes, I want to ask the other members, do we understand what coefficients are, so that we don't assume that we all understand what he's talking about? Other class members, do you understand what coefficients are or is?
Yes, sir.
Yes, sir.
All right, thank you. So you can
Yes, okay.
continue.
Okay, sir. The second row has there's no x there, so the x will be 0 since it has no coefficient. That's 0. Then the y has 1 coefficient, which is 1. Then the 3z has 3 coefficients, which is 3. Then there's 3, which is the constant. Then the next row has minus x, so that is minus 1 as a coefficient. It has no y, that is 0y. Then the last, it has minus 2z, so that is minus 2 coefficient, and it also has 2, so which is the constant. Then to the next step. So if we look at the next step, if we look at the image like that's above step 2, there's something on it, something like R1 plus R2, then R0 to R3. What that simply means is that we are going to be, before we can solve like any Gaussian elimination, then we have to use this, something called elementary row operations. So when we are solving Gaussian elimination, we can use addition, row operation, we can use swapping, we can replace, we can divide. So when we are, and we can also multiply, so as for us to be able to get the result that we are looking for. So in the next step here, we want to start by, we want to, since like in the step 1, we already have like, we have a 0 in the second row, like in the second row of the first column, we have a 0 there. So we want to have a 0 in the third, like in the first row, like in the third row of the first column. So we want to have a 0. That is the purpose of the next step. So if we add row 1 and row 2, if we add row 1 and row 3, then the result of row 1 and row 3, like if we were to add row 1 plus row 3, then the result will be used to replace the entirety of row 3. That is simply the meaning there. So if we were to add row 1 and row 3, let's do an. Hello?
Yes, can you hear me?
Hello? Yes, I can hear.
Yes, what I'm saying, what I want you to explain is when you have maybe in your modified slide for later submission.
Okay.
I think you should add another step where you label the rows so that we know which is row 1, which is row 2, row 3.
Sir.
Because what I'm saying is it row or column that you are adding?
Okay. Please, can everyone see my, okay, I will annotate. So I will annotate to make it clearer. Here, this is our column 1. Please, can everyone see my annotations?
Yes, please.
Okay, this is our column 2, and this is our column 3, and this last here is the constants. Then, so these are the constants. Okay, so once that is clear, let me clear everything. Then this is our row 1. This is our row. Sorry. The diagram is sorry. So this is our row 1 here. So our row 1. Then the row below is our row 2. Sorry, the diagram. And the row below is our row 3. The diagram is just. I'm very sorry for that. But I hope everyone understands this. So I hope everyone understands this.
Yes.
But please, sorry, how did you come across this 1,0,0? This multiplication, when you're adding, that's what is a bit confusing.
Stop.
In your step, you said add row 1 and row 3 to replace row 3. Like,
yes.
Please, sorry, just come again. I don't really get that particular one, please.
Okay. See, when we want to solve Gaussian elimination, since this is the presentation, so like all the thinking, so the thinking has already been done. What I'm just doing is to explain my thinking. If you were like, if somebody else to solve this, they might solve it using different row operations, and that's why I explained before I started that we use elementary row operations, addition, swapping, multiplication, just to get the desired result that we want. So from my own workings here, I'm taking this step. Somebody else might decide to solve this, and let's say you can say, okay, the next thing is to add row 1 and row 2 to give you the result that it needs. Basically, the purpose is to get the results needed, and which I've already explained earlier, which is the goal of this whole process, this Gaussian elimination. So here,
all right, Mr. Abdulrahman.
Okay, sir.
Yes, I think what the question is about is
okay.
You have chosen to add your row 1 and your row 3. Then the solution is going to be replaced by your row 3. And you have also told us that you have also tried to label your rows, right? So the explanation goes this way. If you look at step 1, right? On the first row, you have 1, 1, -1, and 9, right?
Yes.
Then on row 3, you have -1, 0, -2, and 2, right?
Yes.
So according to his formula, R1 plus R3 to replace row 3. Now you have 1 plus -1, right? It gives you 0. The other one, 1 plus 0 gives you 1. Then the other one, -1 plus -2 gives you -1 -2, which gives you -3. So it also applies to, now, are you going to also add the constants?
Yes, sir. Yes, sir.
Okay, so for the first one, you have 9 plus 2 gives you 11, right?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
All right, you can continue. Now, I think, is that a bit clear or risky?
Yes, it is, sir. Thank you.
Okay, sir. So I'll move on to the next row now. Please, before I move on, I want to say something. We should all notice that every next operation will need the previous operation to solve. So what I'm saying is that now step 1 is now it's now obsolete. So the step 2 is what we will use to solve the next step. So what I'm saying is this. So this is the next step, step 3. Now we have gotten 0. Okay, now we have gotten 0 here, 0 here, 0 here, and we have 0 here. So now we want to turn this to, okay, as in before we go to this, okay, sorry, I want to check, I want to show the previous slide. Okay, if we look at the previous slide and the previous one here, you will see that after the step 2, we have 0 here, we have 0 here, but we still have 1 here. So we want to, the next step, which will be the step 3, is to turn this 1 here, to turn it into 3. We take it step by step. So that is the goal of the next step. Now,
yes,
so let's move on.
I didn't get that, please. You said to turn that 1 to 3. How?
No, I said that we have this as 0. Yes. We have this as 0. Yes. Now we want to turn this 1 here to 0.
Oh, okay. You said 3 earlier.
No. So to 0. So let's move on to the next slide. So the step 3 here. So if we were to use this formula, -1 times row 2 plus row 3, the results, so we replace row 3 with the results. Let us do an example. The previous slide here, -1 times row 2 plus row 3, -1 times 0 plus 0 will give us 0 here. Will give us 0 here, 0 here. Then -1 times.
Hello, sir.
Sir?
Are these formulas taken arbitrarily, or is there a method to getting the formulas out?
There's no particular method. It depends on the person that is solving the equation. So it's more of trying to be creative in solving the equation.
Sorry, follow-up question, Abdulrahman. Is the goal to have everything as 0 Like, what's the overall goal?
Okay, this is the overall goal here, to have every number on the diagonal line to be 1 and every number below that diagonal line to be 0. So look at this image here. So we want to have all of these numbers on the diagonal line, everything should turn to 1. Hey, God, it's my annotation. So everything here should turn to 1 and everything below should turn to 0. That is the goal. And if we want to solve it, we have to solve, well, from what I understood, we have to solve, so we start solving from like the first one here, to get this to 0, then we turn it to 0, we turn it to 0, then we try to get the diagonal line to be 1. So we don't start from the diagonal line, from how I understood it. Do you get it?
Yes, that's helpful.
Okay.
Thanks.
Okay, thank you very much. Thank you very much for that. So let's move on. So if we were to apply this equation, this -1, this equation here, if we were to apply this equation, -1 times R2 plus R3 to replace R3, if we were to apply this equation on the previous step, which is step 2, it will give us this matrix. So it will go this matrix. Then for the step 4, if we were to apply this formula here, if we were to apply this formula, so if we were to apply this formula here.
Yeah, I think your slide is missing or something. Or is it only me?
Okay, sorry, sir.
Probably you have minimized your.
Yes, sir.
PowerPoint.
I will share it now.
Okay, we can see it now.
Okay, I'm very sorry for that. So,
young man, you should not be saying sorry all the time. Are you a woman that be saying sorry? Just continue.
Okay. So if we were to apply this new equation here, this -1/6 times R3 to replace R3, if we were to apply this equation on the previous step, on the matrix that we got in the previous step, it will give us our desired matrix objective, like our desired objective, which is to get the diagonal line to be 1, 1, 1, and the numbers below to the 0, 0, 0. If we were to calculate everything, we'll get that exact result. So so after getting this 3 here, this this go here, then we want to solve for we want to write this out in a linear format. So if you can see, I said x plus y. Well, let me say it from the body. So look at, this is our final the objective that we have been trying to get here. So now we have this here in this final equation. So this final matrix. So if you want to write this one out,
hello,
in a linear, sir?
Yes, please. I think for the purpose of presentation, okay, your columns should also be well labeled as X, Y, Z, so that when you arrive at your final matrix, it can be easily seen that your X is, for the first row, your X is 1, Y is 1, then Z is -1 equals +9, right?
Yes, sir.
X, yes, space, Y, and Z.
So, okay.
So it makes it easier for people to see.
So, okay. So if you want to interpret this back to the linear form, you have the first row to be X plus Y minus Z is equal to 9. Because X has coefficient of 1, Y has coefficient of 1, and Z has coefficient of -1. So to be X plus Y minus Z is equal to 9. That will be our first row in the equation. The next row will be Y plus 3X is equal to 3. That will be our second row in the equation. Then the next will be Z is equal to -4/3. That means automatically we already know the value of our Z. So let's go to the next. So if we want to know the remaining values, if we want to know the remaining values of X and Y, we will use substitution method to solve for x and y. So since we already have our z to the minus 4 over 3, then we solve for y, then we solve for z. So this will be our final solution in the problem that we just solved. So x will be 2 over 3, y will be 7, and z will be minus 4 over 3. Is that understood? So I'll move on to the next one now. So the next one here is pivoting strategy. This pivoting strategy is also a form of Gaussian elimination. It's different, but it also uses the same mechanism as the Gaussian elimination. I will see why very soon. It has both partial and complete strategy. It means we have partial pivoting strategies. We also have complete pivoting strategy, and it also uses the augmented matrix formats to represent its equations. So the goal of this pivoting strategy, the goal is to make all numbers below the diagonal line equals to 0. This means that here, we don't care. So this means that here, what we care about here is just these three numbers here. So we don't care about any other thing. So as long, in fact, we don't even care about making the lines on the diagonal line to be 1. We don't care. We just need to make the numbers below the diagonal line equals to 0. This is how. So this is one of the different differences between the pivoting strategy and the mainstream Gaussian elimination method. So I will calculate that. I will give examples of that in a moment. So okay. So I want to make. So now let us solve this equation. This here, we want to solve this equation using the partial pivoting strategy. That is what we'll be using. If we, every single step until you get to the starting stage, it will be the same thing we did with the Gaussian elimination. The first thing, we represented the equation in an augmented matrix format, which is the step 1. Then the step 2, we replaced the row 3 of. Yes, sir.
Yeah, I think your partial pivoting, now you have x1 plus x squared plus x 3 equals 3. Now the next one has 4x plus x squared plus 4x3. Now is there a problem with the value of x? Is it x1, x2, x3?
Okay, sir. That was a mistake on my part when I was creating the matrix in an equation. So this is x1 plus x2 plus x3. It is not x squared or anything. It is x1 plus x2 plus x3 equal to 3. And the other one.
Is anybody taking the notes for those corrections that you're supposed to make?
Please, okay. I didn't notice. I'm just noticing it just now. Even.
No, sorry. Do you have your group members helping you with the notes taking so that you know the correction you're supposed to make when you are submitting your final document? Hello?
Emmanuel. I'm taking the notes myself, sir.
Oh, okay.
Okay, sir. So the one below is 4x1. It is 4x1 plus 3x2 plus 4x is equal to 8. Then the last one is 9x1 plus 3x2 plus 4x3 is equal to 7. It is not square or anything. It's just normal. And it's simply because we don't want to say x, y, and z again. So the x is just like a way of adding something to the number. So we can say x plus y plus z. We can say x1 plus x2 plus x3. It doesn't matter. So it's not square or anything like that. I hope that is clear. So let's move on. So so I said before that step one, as we did before in the Gaussian elimination, we represented the equation in an augmented matrix format in the step one. Then for the next step, we swapped the row 3 into row 1. So we swapped row 3 into row 1. So this means that we swap this 9, 3, 4, 7. So we put it up. So the 1, 1, 1 on top comes down. So this one here, this one here, it comes down to replace the numbers here. So this is this is swapping. This is also one of the elementary row operations that are possible. So this is one of the elementary row operations that are possible when we are solving Gaussian equations. So okay. So move on. So we get our step 2, step 3 and 4, the same thing. We're just trying to manipulate the row operations to get our desired goal of making every number below the diagonal line to 0. The same thing step 3, same thing step 4. Then now in the step 5, now we have the numbers below the diagonal line. Now we have everything to the 0. We have 0 here. We have other numbers are here. We don't care if it's 1. We don't care if it's 2. We don't care. So now to get all of the numbers, we use the substitution method to solve for x1, x2, and x3. So we use substitution method to solve for x1 and x3 as we did in the Gaussian elimination, and that's why I said it's also a form of Gaussian elimination because there are some little differences between them. So as for Gaussian elimination, we have to make sure that all the
there's a question from Miriam Abdul Salam.
Okay.
Is swapping peculiar to pivoting method, or we can also swap in the Gaussian method you explained earlier?
Okay, it is not peculiar to the pivoting method. We can also swap in the Gaussian method that I explained earlier. Do you get that? Mariam?
Okay, she has responded saying yes.
Okay, so, but the next one, we are going to be seeing a difference, which is the LU factorization. The LU factorization, it's also using a similar strategy, similar calculation strategy to the Gaussian elimination. It is also using augmented matrix format as the the results of our LU factorization. It will also be in a matrix format. So the results will not be x is equal to this. No, it's also be in the matrix format. Number 1. Number 2, LU factorization, it's a product of two matrices, which is the matrix L and the matrix U. I will explain that later. Then in this one, we can only use subtraction elementary operation. We can't use plus, we can't use multiplication, we can't divide, we can't swap, we can only, we can't swap like an entire row completely. So we can only use subtraction elementary operations. I will explain that better. Okay, now, what is the goal of the LU factorization? So the goal of the LU factorization, if we please let us look at the screen very well. We want to make, see the LU, as I said before, it's the product of L and U. The L means the upper rectangular matrix. If we look at the L, it must have the diagonal lines must have 1, and the numbers below, the numbers above the diagonal line must be equal to 0. The numbers below the diagonal line can be any number. We don't care. As for the U, the numbers on the diagonal line can be any number. The numbers above the diagonal line can be any number, but the numbers below the diagonal line must be equal to 0. So that's for the U. And also, before we can solve any LU calculation strategy method, the first thing we solve is the U. We solve the U, the upper triangular matrix. After solving the U, we will now use something. I will explain it later. It is from the result of the U that we'll get our L. It means we are not going to be using any Gaussian or whatever for the L. We are simply going to be using the results from what we got from the U to fill in the L. I'll explain. So if we so this one here, it has
Hello,
a popular formula, like
the
formula used in solving the calculation. If we look at, okay.
No, I think your network is breaking a bit. Or is it from my end?
Yeah, we noticed it too, sir.
Oh,
okay.
I see.
So is he now back to normal?
Yes, please.
So can I continue, sir?
You may.
Okay, sir. So if you look at the annotation I made up here, replace Ri by Ri minus KRV. Ri, so this simply means replace so this simply means replace any random row by subtracting that random row by the formula that random row minus R minus K times under random row. What's I want to explain this better. Ri is any random row, Rv is any random row, but the K that is beside the Rv, it is the number that is used to get the result we want in that in that step. For example, if I'm to explain, okay, let me explain so that I will understand what the K means very well. Here, going back to our previous year, we said the goal. So we are solving for the U first. We said that all the numbers below the diagonal line was equal to 0. We don't care about the number on the diagonal line or the number above the diagonal line. So we are trying to make all the numbers below the diagonal line to 0. That's what we are solving for now. So we are solving for U, not for L. So from here, if we look at, this is our original equation. This is our original problem. This here is our original problem. So if we were to apply, so we want to turn 5, 4, and 1 into zeros. So if we say R2, we are starting from row 2, which is 5 here. So if we say row 2 minus 5 over 2 times row 1, row 2 minus 5 times row 1, let's try to solve it here. Row 2 is 5 here, right? So the first one in row 2 is 5 minus row 2 minus 5 over 2 row 1. 5 over 2 times 2 is 5. So 5 minus 5 is equal to 0. So that will give us 0 here. And the next member of the row is 4. So 4 minus 5 over 2 times row 1. So row 1 here. So here we have 2. So 4 minus 5 over 2 times 2. 5 over 2 times 2 is 5. So 4. Sorry. So sorry. The second number. The second member of row 2. Hello, sir.
Yeah. Well, I feel that why you are struggling to explain is because you skip some steps that ought to have been made available to the class members. Of course, this as it stands is understandable, at least for any higher level student. However, for the purpose of simplification, I feel that all you have done should also be written out so that at least anybody following, maybe even a secondary school student, can follow what you have done easily. Of course, it is something that they can do to evaluate. But however, your explanation will be minimal if you do not go step by step. And also in my own grading, I think step by step also counts a lot. It's not just that you know the answer, or you have to tell me if you are substituting, if anything is changing in the next calculation, you should tell me why it is changing, what you did, why it's changing. Maybe it may just be half mark or 1 mark, but at least it has added to your grade. So you may continue.
Okay, sir. The first calculation that we use here is R2 minus 5/2 times R1. If we use calculation on our on our original equation here, it will give us 0, 4, and 5/2. The 5/2 here, the number here is our k value. This is our k value. So the k value from turning this, for making this to be 0 is 5/2. So we record that. That's our first k value. And the second k value here, we want to turn this, so to make this to be 0 also, to turn this to be 0, because before it was, because earlier on it was 1. So here, it is 4 here. So we want to turn this 4 to 0. So to turn that 4 to 0, we use R3 minus 2 and 1. If we use it here, it will turn this to 0, minus 3, and minus 4. So this minus 2, this 2 here is our k value. We record that k value also to 2. Please note, the first k value is 5/2, and that is what we use to get the first 0 here. The second k value is 5/2, and that's what we also use to get the next 0 just below it. Then the third one here, if you see something like R plus 3/4, R plus 3/4 R2, and I said before that we can't use plus, right? That we can only use substitution row operation. Actually, it's not a plus, it's a minus. It's a minus. So what we did here is R3 minus bracket minus 3/4 times R2. So R3 minus bracket minus 3/4 times R2. So minus times minus.
So why was that not stated explicitly in your slide?
It was
well, I feel that some of this oversight that you have done,
yes, sir.
I hope that you're going to make corrections on them.
Yes, sir.
Before you turn in your slides.
Yes, sir.
All right, thank you.
Yes, sir. So here it is R3 minus bracket minus 3/4, then minus and minus will give us plus. That is how we got R3 plus 3/4 R2. If we use this equation here, you get 0. So this equation, this last equation here, is what we use to get the 0 that is here. So which means that the k value, that is minus 3/4. So the k value that was used to get the 0 here is minus 3/4. So which means the first k value is 5/2. The second k value is 2. The third k value is minus 3/4. Note the k value, because that's how we will get our L. Okay. So now we have our U. So now to get our L, I said before, the first k value is 5/2, which was used to get 0, like in this place when we're discussing the U. The second k value is 2. This was used to get 0 here in our U. And the third k value, minus 3/4, which was used to get 0 here in our U. We will start it back to our L. So if we start it to our L, this will be 5/2, 2, and minus 3/4. And as I said before when I was discussing the L, that this is all we need. So the L, the numbers on the diagonal line has to be 1, then the other is 0. So we don't care about that. We only care about getting these 3 k values here, which is what we use to complete our L. So which is what we use to complete our L. Now we have our U. So have our U, we have our so have our L. So we will now write A is equal to LU. Where with this being our L, so this is our L, this one here is our U. So that is for the LU factorization. Then I will move on to the next presenter. Emmanuel.
Yeah, thank you. Can you hear me? Can everyone hear me?
Yes.
Hello? Okay. So thank you, Abdulrahman. So the next topic we'll be discussing is the residual correction method. Okay, so this method is used for solving a linear system, just like the other methods which my colleague here has discussed. We are direct methods. So we had the Gaussian elimination, we had the LU factorizations. All those ones are classified under the direct method. But for this one is you can call this one an iterative method. Okay, so we have two methods. We have the direct methods. We have the iterative methods. So it's as you can see, an attractive feature of the linear system is that the error involved in the approximate solution when compared to the exact solution. Remember what we did? I think the last group that presented a week ago, where we talked on error approximations and all. So we will still review some of those things as we move forward. So what we have here is our A, which is the matrix, the square matrix, and then the E, which is the error, okay, the mathematical error, and then the R, which is our residual. But we'll know how we got that when we move forward. So there is a difficulty in the process of obtaining E, especially on a computer. What this is saying is that on computers can never give you the exact thing you want, because there are different types of computer. Calculator is a computer. Your normal laptop is a computer. So no matter what, most of them will get to truncate it at a point after solving to a particular value. They get to truncate it. So you will never get you will always have a sort of error or a residual. Let me put it that way. So this is the next slide. Okay, so the basic definition is, for example, if an n by n system of linear equations, that's ax equals b. This is just a linear equation, as we all know, and it has a unique solution x, and the x here is our the x here is our exact solution, and the x star is our approximate solution. Okay, so let's assume that's a computer solution. Then the residual is the difference between B and the matrix A. The difference between B and the matrix A. So the B there is our vector. Okay, is our known vector. The B is our known vector. Sorry, the B is our known vector. So multiplied by our computed solution, which is the approximate solution which we have gotten. So what we'll get is, I would say, is like a formula, or like after using the algorithm, you get R equals B minus A, then X star. So what we need to know what these are. The R is the residual, the B is the known vectors, and I'm sure we know what the others are. A is the main square matrix, and X is the approximate solution. So error is given as E equals to X minus X star. So it should be noted that both the residual R and the error of the approximate solution are matrices. So everything we are dealing with in this AX equals B, they're all matrices. We're not just talking about values. Maybe A is 5, X is 2. No, all these things are matrices. I've said what they are, so I'll not repeat myself. That is our computed solution and our exact solution. So X star has no error, and furthermore, the residual is given as R equals B minus A X star. So you can also see equal to B minus AX equals to 0. What this means is that, just look at it, just focus your mind on the R equals B minus AX star. So that is our formula. That's the formula we are working with. So remember that this AX, is sorry, hold on. Finding difficult to. Please, let's move to the next slide. Hopefully, I continue it from there. Okay. So this is the continuation, like definition of the residual. So residual R equals B minus the AX, where X is the imprecise computed solution. So imprecise means the approximate solution is not precise. So the error E, which is a mathematical error, is the actual solution minus the approximated solution, that is X star, where X is the exact, okay, X is the exact, that has given the definition. So the relationship between the residual and the error, R equals B minus AX, is equal to AX minus, okay, this is what I wanted to explain. The R equals B minus AX star is equal to, remember that our AX is equal to B. If you can remember the linear formula, AX is equal to B. Then we are substituting that B with AX. That's why you can see equal to AX. So we are substituting B with AX, then minus the AX star, which is still on the formula. So the next thing is A is common to both sides. So we just pick out the A. So please can we go back? Thank you. So the A is common to both sides. So we just picked out the A and then we put this X minus X bar. And don't forget that our mathematical error, the formula for our mathematical error is X minus X star. That is our exact solution minus the approximate solution, which is the E. So we can just substitute that X minus X bar with E. That's how we got the AE. So in the end, you have something like R equals AE. So this motivates the definition of the residual correction method, where the corrected value, say X of C, is given by this. So this X of C, this C that is there is just like the initial value of X, the initial solution you get for your X. It's almost like the approximate solution, but this is the initial one you get, because since we are dealing with iteration, we'll do many processes, we'll get many X, we'll get X1, X2, like that, till where you decide to stop. So this XC is given as the initial value of X. This is next. So how can we tackle problems with this method? So this method uses residuals in order to reduce the error between the X star and the X, which is the approximate solution and the exact solution, with each iteration applied. So this is the main goal of using this method, this iterative method. So the steps to solving with residual correction method. So let X not equal to X star. So the X naught I said, remember where I said XC? C is just a representation. So now X naught is the first value of X that we got, the first approximate solution of X. As you can see, X naught is equal to X star. This X star, you can get your X star is not just something invisible. This X star is, if you use your Gaussian, you can use so many of the direct methods to get this your X star. You can use the Gaussian method, you can use the LU to get this X star. And when you get this X star, it's the same thing as this your X naught. Okay, so let X naught equals X star. That is, let the initial computed value for X in solving the system AX equals B. We can define the residual as this. So you can remember the formula R equals B minus AX. So this is R naught, that is the initial, equals to B minus AX, then the initial X naught, that's the initial value we get, okay, from the Gaussian. Whatever you get from using your Gaussian or any direct method, that is going to be the value of your X naught. So we have R naught equals, you simplify for that. Remember your B is AX, then minus this, that, you get to this point. It's the same, I've explained this before, but this we are dealing with the initial. So this is like what we get first. So you see, as we move forward, we will get to a point where we get R1, R2, like that, depending on your residuals or the residuals that are there. Please, the next one. Okay, so this step 2, we then solve for the E naught. Note that E naught is the actual error between your X star and the X. Okay, that's the actual error or the mathematical error between the actual solution and the approximate solution. So in solving for E naught, we obtain an approximation of E naught. We are denoting it as E star naught. We are denoting it as E star naught equal to, this is an approximation sign. So E star naught is equal to is approximately the same thing as E naught. So when we then use this value E star naught to improve our approximation. So let me just explain this. So we know our error is equal to X plus the X star. That's the X which is the actual plus the X which is the approximation. So please, if you sorry about this, I just made an annotation there that E star is also E with cap. Okay, so this is an image. I could not change it. So if you see E cap, just know that it's still talking about E star, which is the approximate error in this case. So then we can define another residual as, so this is still repeating the same thing like I said. Remember the first one we did was the first residual with R naught. So as we're iterating, the next one we'll look for R1 like that. So it's still the same formula, R equals AE. This is the next one. Next slide, please. So for step 3, when we then solve for E1 as the better approximation of the actual error E naught. Okay, so that's the next step. To get a better value, keep on solving, keep on moving forward. So to get our error approximation E star naught, we can then use this value E star 1 to improve our approximation by letting, so this is still the same formula, but now we have iterated further. We'll see that when we go to an example, hopefully. So finally, we can of course continue this process until the desired level of accuracy is reached. So you can iterate till even you get X4 or X5, depending on what you want, or depending on if it's getting closer to the solution you got from your Gaussian. Please, the next slide. Okay, so this is someone has a question. Please, Michael.
Okay, please. I just want to confirm something. The purpose of what is the what is the overall aim of this residual value error? I know you said it, but can you just make it like an example? Like, why do we have to understand this residual correction method? What purpose does it serve?
Okay, thank you, Michael. When we get to the example, I think we'll better understand. But the main purpose is to reduce the error between our X star, which is our approximate solution, and the exact solution. You know, there's going to be an error when you have an exact. You're supposed to have an exact solution, and then most of these solutions we get on our calculator on the computer, they're not the actual solutions. They're just approximate. So using this is going to reduce the error which you get when you are trying to calculate for any system of linear equation. So the reason why you might see as you are using Gaussian, and we might be getting values like x1 equals 2, x2 equals 3, x3 equals 4, and those are looking like exact solutions. Yes, you might get exact solutions at those points, but when you start working with things like decimal or fractions, then this is a correct, because at a point you have to truncate. So this is just to, like I said, to reduce error between your X star, which is the approximate solution, and your exact solution, which are supposed to have with each iteration applied. I don't know if that's clear. Maybe when we go to the example, is that a bit clear?
Yes, thank you.
Okay, so hopefully when we get to examples. So this is the algorithm to follow. So we have an input. So our input is going to be gotten from us using the Gaussian elimination method. Like I said, it's a direct method. So our X naught is the same thing as our X star. Remember I said this, anywhere you see this X cap, is the same thing as X star. It was just, I was supposed to change it, but this is an image, so I could not do that. I apologize for that. So your X naught is equal to your X star, which is your approximate solution, which you must have gotten through your Gaussian elimination method. So AX is equal to B. We have a tolerance of elements greater than 0. So let R naught equals to B minus AX naught. So that's the formula, R equals B minus AX. But since we are starting with the initial, we are using naught, R naught, and then X naught, because we are starting with the initial before we move further or iterate further. So the next thing to do is solve for E naught, satisfying the A E naught equals R naught. So the A is your spare matrix. The E naught there is your is the error which you might have gotten, and then the R is the residual. Then while the absolute value of En, that N is just like any values 1, 2, 3. So while the absolute value of En is greater than the elements, do this. So this is just a step from this while this is showing a sort of iterative process. So if you have this condition, you iterate further. If not, you end the solution. So let's go to the example. I think from there we'll be able to understand how this algorithm is applied. Okay, so this is an example. Sorry, I didn't want to use a direct value, like maybe instead of all these decimals, I didn't want to just use whole numbers. As I use decimals so that you understand that iterative. Ordinarily, if you just see a solution like maybe 5x1 plus 2, just like Gaussian, if you see it's a problem as such, ordinarily it's faster to just go ahead and use Gauss-Seidel, but not Gauss-Seidel. It's faster to use Gaussian elimination. But when you have something like this, it's advisable to use something like this, an iterative process like Gauss-Seidel. There are so many other iterative processes, not just this particular one. So we say using a computer with 4-digit precision. So the computer can be a calculator, a small calculator that just has a 4-digit precision. So your answer is going to give you 4 digits. It's not giving you more than that. That's what this is saying. So when you're using that particular calculator or that computer to calculate, or using Gaussian elimination to solve this particular problem, it will give you a solution of this. It's 8.968, like that. These solutions, and these solutions are, take note, these solutions are for x1, x2, x3, or the unknown values of x1, x2, x3. So let's assume you've used your calculator. This is what you got for the initial value of x, which is, remember, an approximate solution. It is not the exact solution because we can't really get the exact solutions, especially when we are working with decimals. We know ordinarily that this is supposed to give us more than 4 digits, but because of the computer we are using or we used, it gave us just 4 digits. So this is our approximate solution after solving this using a calculator. Please move forward. So now, I hope you can see the algorithm. Sorry, I just put it like that to close with this. So following the residual correction algorithm, taking the elements as 10 raised to the power minus 4 and giving our approximate solution as this. So we have gotten our approximate solution, or they gave us our approximate solution. Maybe we might have gotten using any of the iterative or direct methods. So now to get our residual, which is R.
Hello, please,
remember,
can you go to the equation you are solving?
Okay. Please go back.
All right. So how did you get your x naught? Can you explain again? To be 8.968, this.
Yeah.
How did you arrive at that?
Yeah. So this is, I didn't solve it here because it's saying using a computer. So it's assuming we are using a computer to solve this problem. You can use a calculator. You can decide to use Gaussian elimination to solve this problem, as he explained, as my colleague explained earlier. You can use Gaussian elimination to solve this, whereby you just pick out your x1 as 0, your x2 0.5, your x3 0.333. That's your first row. Then of the matrix, of the singular matrix. Then the next one, the row 2 is 0.5. You pick out the next one, 0.33. Then you can use Gaussian elimination if you want to solve it. But there are ways computers now can solve this for you and get an answer. But they might not give you the exact answer because of the limitation that they've given us. They said the computer we used is the 4-digit precision computer.
So how will the computer solve? Hello, how will the computer solve it?
Okay, so this was not really, it didn't really tell us the computer that solved it. But if we are using maybe a laptop, there are computers there are programs or softwares that you just need to impute the value.
And what is that software?
I know there's Maple and the other softwares, but someone could, just using that particular algorithm which I just showed you, someone could, once you code that particular, you can just code, someone can code create a code that solves Gaussian. All you need to Gaussian elimination. Someone can create a code or a program that
if I give you this equation and I say you should employ Gaussian elimination method, you should solve it, and I didn't give you X naught, how do you go about it?
Give me X naught, I will use Gaussian elimination to solve for my X naught or Gaussian, depending on I can use Gaussian elimination just like my colleague, and then you get our X naught, which is the values. The first one is your value of X1, the next one is value of X2, and the last one is the value of X3. You can use Gaussian elimination to get your X naught.
Well, I'm not convinced anyways, but you can continue.
Okay. This is the next. So having used Gaussian elimination to get your X naught, which is 8.968 minus 35.77 and 29.77, which is the initial value of your X, the approximate value of your X, your X naught. Then we are trying to look for the residual. That's the initial value, which is R naught. So we recall that from this algorithm, we are using to get our to get our R naught. Our R naught is equal to B minus A X naught. Okay, remember I stated this formula in the beginning. So we are using this to get our residual. So we know our B. Our B is our known vector. If you go back to the example, you see that our B, you know the values of your B. Then your A, you know the values of your A.
Yeah, can you go back and show us where you are getting your B and where you are getting your A?
Okay, please go back. Okay, so like this now. No. Please, to the example, the question. Okay, so our A, remember our A.
Hello, can you share your own screen so that you'll be able to work at your own pace?
So my computer just went off. So I'm using my phone. I don't know if I can.
Yeah, but your explanation is not sound enough and it's not deductive. That's why I'm having issues with your presentation. Yeah, where's your A? Where's your B? You just say when we get A, when we get B. That's too vague.
Okay, let me take it slow. Please go back to the question. Let me take it slowly so that hopefully the example, please, the example. Okay, thank you. No, please, the question itself, sorry, the question is okay. So now I want to explain, you have R equals to B minus AX naught. So we are trying to find R, and remember that our A, to get our A is already given to us. A is the singular matrix. Just like if you have if you are solving a Gaussian elimination question, you have this is the way it will look like. If you are trying to solve a system of linear equations, this is how it will look like. Your A are these coefficients. Let me put it like that. Your A is this question and form your 3x3 matrix as your A. I don't know if that's clear to everybody. To get your A is just to pick out the coefficients from these questions and form your 3x3 matrix where you have for the first one, you have 0, 0x1. So 0 is the first coefficient. Then the next one by side is 0.5. Then the next one is 0.333. Then under it, you are forming a square matrix that way. Then under it, you have
No,
0.5.
the first coefficient should be 1, not 0.
1, sorry. Sorry about that. It's 1. 1x1. So the first coefficient is 1. Then that way you form the square matrix. I don't know if that is clear to everyone.
That's your A, right?
Yes, that's my A.
So why didn't you present that in your slide? You say, okay, to get A, take the coefficient and say A equals, you now form that matrix set equals A. So where's your B?
So our B is this, the known vectors, that is this 1, 0, 0. So our B is just going to be how do I call it? But it will be in matrix form, 1, 0, 0.
Your what? No, that's what?
That's our B value. Just like
Is what?
we are following is 1, 0, 0. Following the.
How did you arrive at 1, 0, 0?
Looking at this question, you can see the first value is equal to 1. The second one is equal. The second equation is equal.
You don't
to 0.
use value. They are equations.
Yeah, sorry. The equations. The first equation is equal to 1. The second equation is equal to 0. The third equation is equal to 0. So all this 1, 0. Yeah, thank you. This 1, 0, 0. These are your B values.
Okay.
So this is just following the AX equals to B, where you pick your A as the square matrix. The X value is all these unknown values of X1, X2, X3. And then the B value is this 1, 0, 0, the known vectors that we know.
Yeah, so how do you just assume that everybody understands what you are saying without any form of explanations? Yeah, continue.
This is the next slide. So it says let R naught equals to B minus A, then X naught. So I've explained what our B is, which is that vector, the 1, 0, 0, then minus A, which is the matrix we got. And then the X naught is going to be this one, which we can see here, this particular matrix. This X naught equals 8.968 minus 35.77. You must have gotten this one using your Gaussian elimination, if you will. So you just slot it there.
What is that T at the back of that equation? What's the T for?
I think it's just showing that it's like a transpose. You can transpose it if you want, either as a row vector or a column
You are
vector.
not sure. You should go and find out. Your explanation is not.
Okay.
We understand up until you have let your R naught equals B minus AX naught. Now that AX naught, are you replacing the values of X with the values of X naught?
These values of X, this X naught, we are using this X naught that we've gotten using our Gaussian elimination method.
Where are you putting it? You have your AX to be your your matrix, right? And your B.
No, yeah. No. The A is just the square matrix.
Okay.
Yes. Then
So
this
where is
X
that
naught
X in front of it from?
This is X naught. X naught is not just X. This is X naught. X naught is
Hey,
the
hello,
value
please
we've gotten.
listen to what I'm saying. Now, the first algorithm says impute X naught to be equals to X cap obtained from using Gaussian elimination solution, right? Now, AX equals to B. Where did you get that X from? AX equals to B, line 2.
Okay, that is just the normal system of linear equation. That's like how it's going to look.
Okay, so the value A is a coefficient.
Yes, the value is the coefficient. Yes.
X equals B, right? So once
Yes.
tolerance level, which is an element greater than 0, let R naught to be equals to B, right? We know B minus
Yes.
A X naught. So are you going to be substituting the value that you have 8.968 as X naught for the first instance, or what?
No, we are going to put these values, this 8.968, comma minus 35.77 and 29.77. These are the values of this is like x1, x2, x3 that we got from using Gaussian elimination to solve the question. So we are just imputing everything there as x naught as a matrix itself. We are just putting everything there. So in the end, we'll multiply it with matrix A. So it's going to be like a square matrix multiplying a normal row matrix. I'm sorry,
But
maybe
I think
I'll try
spell
to.
that out very clearly, because that's what is wasting our time on this presentation.
Yeah,
You're just
I'll add it so that.
assuming that we should be thinking out of this thing. That's why you should explain clearly, just in simple time, I would have moved on. But you have made it so cumbersome with your. Okay, continue.
Okay, sorry, I'll add that. Find a way to add that so that it's clear. And then solve for E naught. So next one we are getting our E naught, satisfying the equation A E naught equals R naught. So our E naught is to get our E naught, you can just substitute. We know what our A is, we know what our R naught is, having done the first step, which is R naught equals this. So we just substitute and then we get our E naught as it is. Maybe I'll make it more explanatory by writing it out. So our E naught there, everything we are dealing with, we are working with matrices. So it could be a square matrix, it could be a row matrix, and it could be a column matrix. So we are working with matrices, everything that we're doing. So as I'm saying, substitute. So this area substituting it's a square matrix, which we know what our A is. This E naught is what we are looking for. And then this R is already known. This row matrix, this minus 0.0053. So in the end, we'll multiply it and then get the value of our E. I think I'll maybe add a slide
Yeah,
to
I
do the
think that's
explanation
your
further.
x raised to power 0, x raised to power 1. Is it to base or raised to the power? Oh, okay, I think I've seen it in the algorithm. Continue.
So when you do this, you would have gotten your R naught, your E naught, your X naught. Then from there, you move to the next iteration. So as you can see, the X naught, the second X naught we got was using this iterative method was 9.060 and 36.31. Then the next X1 was using the same iteration step. The next X1 was 9.062. So you can see it's somehow increasing.
Sorry, how did we get the X notes?
Hello?
Can you hear me?
Yeah,
Please,
I
I think you should remove your earpiece if you are using one so that we hear you clearly. Your question.
Oh, okay. I was asking how you got the X naught. The new one, the one that starts with 9.060.
Okay. So looking at is following the next step, the looping step. So we've gotten our R, we've gotten our E. So using this, the next step, xn plus 1. Okay, so that is, this is not supposed to be there. This is not supposed to be there. This x naught is not supposed to be there. We already have our value of x naught. Sorry about that. It's not supposed to be there. It's not
So
supposed
that's
to be
your
there.
first, that should be your first iteration, which should be x1.
Yeah, yes, which should be x1. Following this, the algorithm. Is the next slide. So the next one, this is another subtopic, conjugate gradient method. So this is another iterative method of solving linear equations. It's like the most popular one that is used, and it's suited for solving sparse matrices with certain properties. And in practice, we generally don't use dense matrices of a huge dimension, since the huge matrices often arise from discretization of differential or integral equations. So this conjugate gradient method, we use this when even solving partial differential equations and all. So that's what this second and third point is trying to explain. But the main thing we need to know is this first one, which is like the popular method for solving linear equations. Here's the next one. So an example. So consider the linear system AX equals to B. This is how it looks like, where your matrix 4, 1, 1, 3. This is your square matrix A. Then the X is X1, X2. Okay, and then the B is your known vectors 1 and 2. So we will perform 2 steps of the conjugate gradient method, beginning with the initial guess. So this one, there's always a sort of initial guess to get your X naught. Okay, there's always a form of initial guess, or if you use your Gaussian elimination method, you can still get your X naught, as I explained in the other part. Then in order to find the approximate solution, and remember, any solution we are getting is always the approximate, not the exact. We can't really get the exact solution. So all the solutions gotten from any of these direct or iterative methods are
Mr. Emmanuel, I've been wondering that was that your Gaussian? Is Gaussian? I was wondering that where are you getting Gaussian from? Or am I the one mistaken?
Gaussian elimination.
Continue.
So using, please, next slide. So for reference, the exact solution is D. So using okay, so this is showing us our exact solution, which is X, but our approximate solution is X naught. So assuming this is the exact solution, this is our exact solution, 1/11 and then 7/11, having solved the equation. The next, our first step is to calculate for the residual vector R naught and associated with X naught. The residual is computed. So we can remember this formula from the formula R naught. Sorry, this naught is supposed to be up, it's supposed to be a superscript, not a subscript. It's not supposed to be on the bottom. I would think that R naught equals B minus A X naught. And in our case is equal to this. So this is solving. Please, can you go back? Okay, you can go. Please go for. Please go back to the slide where I was. Okay, so using this now, this is our B is from that our question. Our B is 1, 1, 2. A column vector 1, 2 from that equation. If you go back, you see 1, 2, then minus our A. Our A is 4, 1, 1, 3. Then our X naught is what we've got in there, what I showed you using any of the methods, Gaussian or using Gaussian elimination, you get the X naught. Okay, so when you solve this, you can multiply this now. To multiply this A and X naught, you do the first row, that is 4, 1, and the second, and this singular, this column vector, that is 4 times 2 plus 1 times 1. Sorry, I cannot annotate because my laptop is dead, but I hope I'll take it slowly so we do 4 times 2 plus 1 times 1. So we'll get a value. Then the next one is going to be 1 times 2 plus 3 times 1. So you are supposed to get just a column vector on its own. Okay, when you multiply this, you get a column vector. So when you get that column vector, you now do 1, 2 minus that column vector. Okay, this matrix 1, 2 minus that column vector. This 1, 2 is also a column vector, a straight. So you do 1, 2 minus that one. And then in the end, you get minus 8 and minus 3. So that's the value of R0 in this sense. So, and it's saying this, what this is telling us here is also that our R0 is the same thing as our P0. So all these notes are supposed to be superscript. Then since this is the first iteration, we'll use the residual vector R0 as our initial direction, P0. So to say this particular one has a sort of formula, let me put it that way, which is this, which you can see below here, alpha naught equals to, okay, I think the relationship alpha naught equals to R0 transpose R0 over P0 transpose A P0. So we have the values of our R. Transpose just means you will change if it was a row matrix, you change it to a column matrix. That's the meaning of transpose. So as you can see, we have our P0 as minus 8. Just look up at this page. We have our P0 as our minus 8 and minus 3, and it is a column vector. So, but because we have transpose, we have T here on top of this R0, using this relationship or this formula, it's going to switch to a row vector. It's going to change the way it looks. While the other one will remain the same way, the R0 does not have a transpose. So over then the P0, which is the same thing. Remember, R0 is because P0. So, but it's going to be a transpose of the T there. So we transpose it. Then A, we put our value of A, and then the P0. Then when you, I don't know if okay. Then when you do everything, when you multiply and get your solution, you have 73 over 331 as the answer to, as your alpha naught. This is the next slide. So we can now compute x1 using the formula. Okay, so this is our initial, second, we know we had x0 before. So now we want to get our x1. So we are using x1 equals to x0 plus alpha naught P0. So everything is just substituting. We're just substituting, working with the relationship. We'll just be substituting. We know the value of our x0 as we had in the beginning as 2 and 1. So we just put it there. We just recently got our alpha naught as 73 over 331. And then our P0 as minus 8 and minus 3. So you multiply it, you do 73 over 331 times 8, you get a value for the upper side. Then 73 over 331 times minus 3, you get the other value. So once you add the two matrices, the two column matrices, you will get this value. So this result comes. So I think then this next one is still the same. We are trying to get R1 in this case. So I think this is the second iteration. Remember the first time it was R0 we got. Then this one now we're getting the next iteration, which is R1 superscript, not subscript. Everything here is supposed to be superscript. The next one, please. Next slide, please. Yeah. So this is everything here is just continuous iteration. We just kept on iterating, and yeah, so I think beta, there's a value. So we are trying to look for, the goal is to look for the alpha and the beta. So beta, this is the relationship for beta, or the formula, we call it formula or relationship for beta. R1 transpose R1 over R0 transpose R0. And then just substitute. We've gotten our value of R1 before. You know how to do the transpose. You just substitute everything and then calculate, you get that final answer. And then now using this scalar B naught, we can compute the next set direction P1 using this relationship. So this is another relationship or a form of formula, and then you just substitute the values and get your final value. Sorry if this particular one is kind of sort of difficult to explain. I couldn't really grasp it immediately. It took time. So let me just apologize for that. This part was difficult to put down and also explain. So so I guess I'm done with that particular one. Ill condition metrics, please. My other colleague. Okay, when do we stop iterating? Please go back. Please, yeah. No, please go back. Go back to, yeah. So the result X2 is a better approximation to the system solution than X1 and X0. So we iterated to point X2. And he said if the exact arithmetic was used in this example, instead of limited precision, then the exact solution would theoretically have been reached after n equals 2 iterations, n being the order of system. So I think once the solution is looking closer to what we had as our exact, if you go back, once it's getting closer, you can just end the iteration, except it's just keep going on and on. So I think once it's getting closer, I think you can just end the iteration. The next topic. Hello? Hello? This next.
Okay, thank you, Emmanuel.
I think Modifier might prefer to share his own screen, or do you want to use my screen?
We can continue using your screen, but if you want me to share mine, that's fine. Anyone is fine by me.
You can continue.
Okay, good afternoon, everybody. I'm taking the remaining topics in this. Okay, my colleague still has one more topic, but we'll try to hold it after this because there are some things here that will be needed in Zonda's growing theorem. Okay, can everybody hear me clearly?
We can hear you.
Okay, all right. So the first topic is ill condition matrices. Now, what is a new condition? Let's talk about a new condition system before we make it peculiar to a matrix. Now, when you say a system is ill conditioned, condition. So now let's look at this equation: x plus y equals 2 and x plus 1.001 equals 2. Now, if you solve this equation, the answer is x equals to 2. The answer is x equals to 2 and and y equals to 0. Now let's make a little, you can go to the next slide. Now let's make a little change to the equation. For example, let us make the previous equation was x plus y equals to 2 and x plus 1.00y1 y equals to and x plus 1.001y equals to 2. Now we now added just 0.001 to the output of the second equation, right? So it's not 2, it's 2.001. Now when you solve this equation, the value of x is now 1 and the value of y is 1 from x equals to 2 and y equals to 0. So that means that a very minute change in the coefficient, now it doesn't have to be the coefficient of x and y, it could also be the result. So a minute change in the result of an equation drastically affected the entire system. So it means this system is ill conditioned. it means this system is ill-conditioned. So that is now what we mean by a matrix too. So we can see an ill-conditioned matrix will now mean a matrix where a small change, a very minute change, for example, in this case, 0.01 drastically affects the solution of that condition. So the corresponding matrix used to solve the system of linear equation will be an ill-conditioned matrix. So next slide. So now there's something called a condition number, right? So now in the field of numerical analysis, condition number of a function measures how much the output value of the function can change for a small change in the input argument. That is, if we have an equation, if you have a function, right, and you make a very small change, how much does it impact the output? That is what we refer to as a condition number. That condition number will make you to realize if it's a conditioned matrix or an ill-conditioned matrix. So it's used to measure how sensitive a function is to changes or errors in the input and how much error in the output results from such an error. So let's say, like the example I gave, it was supposed to be x plus 1.001 equals 2. We now made an error and said x plus 1.001y equals to 2.001. Just that small error changed it from x equals to 2, y equals to 0 to something as big as x equals to 1, y equals to 1. So now the most well-known example, no, please hold on. The most well-known example, so there are actually different ways of calculating condition number depending on the function or the system we are talking about, okay? But in this case, we're talking about a matrix, a linear matrix, n by n matrix. So the most well-known, that's the focus here. So the most well-known example of condition number is condition number of a non-singular square matrix, which is modularity of A and modularity of the inverse of A. Next slide. So I think we already explained this. So now, condition number of matrix tells how sensitive a multiplication with the inverse of this matrix based on the formula I just showed. So the condition of matrix tells us how sensitive when you multiply that matrix with the inverse of this matrix, the change. So it tells us how sensitive multiplication with the inverse of this matrix is to a small change in its multiplicand. So it means, so what we're saying is the higher the condition number, the higher the sensitivity of the matrix, right? So a matrix is said to be ill-conditioned when its condition number is significantly greater than 1. So if you calculate the condition number of matrix and it's like maybe 1,000, 4,000 and something, then that matrix is ill-conditioned. A 4,000 condition number matrix is more sensitive than the 1,000 condition matrix. Now, a well-conditioned matrix, we have a condition number close to 1, either approximately or 1 itself, or very close to 1, maybe 1 point something, or even let's say 2. But the moment we begin to have large condition number, then that matrix is ill-conditioned. So next slide. So now, next thing for me is supposed to show how to calculate condition number of a matrix, but I would skip it. I will do it after because I want to talk about metric norms. Metric norms would inform how we calculate the condition number of matrix, because the normalization of the matrix will determine how we go about calculating. Like I said, condition number of matrix, it does not have one straight formula. It's dependent on the system that you are working with. It's dependent on the function and all. So we can have condition number for a quadratic equation. You can have it, like the example I gave was for a simultaneous equation, right? So it's dependent on the system. So I want to talk about metric norms first. So now, the norm of a square matrix A is a non-negative real number that is denoted by this. Now, we noticed this was in the condition matrix formula. So that's why we need to understand what it means first. So this is my second topic what I was giving. So there are different ways of defining a matrix norm, right? You can define a matrix norm. We'll look at those examples, but in whatever normalization you define a matrix, it must follow these 5 principles, at least basically. One is that the norm of that matrix for any square matrix, the norm must be greater or equals to 0. So you cannot have a negative norm, right? When you find the norm of a square matrix, notice we said square matrix, that would be n or n by n matrix. It will be a 2 by 2 or a 3 by 3 or a 6 by 6. So when we find the norm, it must be greater or equals to 0 for any square matrix A, right? Now the norm of a matrix will be equals to 0 if and only if the matrix itself is equals to 0. Okay. The third one is that when you multiply the
hello, sir.
Sir.
Yeah, well, I appreciate your thoughts, but I think we have 8 minutes now to the end of the class, and immediately I have another class.
Okay,
so
sir.
I don't know, will 9 minutes be sufficient for you to complete your thoughts, or you finish it by next week?
We have the topics. I doubt that my previous colleague still has one more topic to talk about, so I doubt we'll be able to do it in 8 minutes.
Okay. Probably you take the first half of the next class, or maybe just 30 minutes to conclude your thoughts.
Okay, sir.
Then the other fellow for, I think, group 4, so we continue immediately you are done. Is that okay?
Okay, sir. Yes,
then,
sir.
of course, Mr. Emmanuel will also present his thoughts again, at least just to clarify the gray area. Yeah, where he will spell out all the assumption that he did. So probably you could just complete these thoughts and let's see how far we can go before it's 3 o'clock. Thank you.
Okay, sir. So I should continue. Yes,
please.
Okay, so third rule says when you multiply the matrix, a norm of the scalar, or the norm of the matrix with a scalar must be the same as the norm of the matrix and a, what's the statement again? So please, can you let me go to the previous slide and to check something? No, previous, I said previous. Previous, next one, just one more. Okay, yes. Okay, thank you. You can go back to my slide. I wanted to show I didn't skip a slide. So the third rule says that when you find the norm of the matrix and a scalar, it must be equals to the modulus, the norm of the matrix alone and the norm of the scalar. That is, the scalar should not have any significant impact on the properties of the matrix. The fourth one is if you pick two matrices together, you sum two matrices together and you find their norm, it must be less or equals to when you find the norm of each of those matrices independently and you add their results together. Okay, so it's more like saying the norm of A plus B must be less or equals to the norm of A plus the norm of B. All right. The last one says that the norm, when you multiply two matrices, when you find the product of two matrices and you find their norm, they must also be less or equals to when you find the norm, when you find the product of their individual norms. So the norm of a matrix is the measure of how large its elements are. So it's a way of determining the size of the matrix that is not necessarily related to how many rows or columns the matrix has. So the norm of a matrix is a real number. So let's just go because of our time. Next slide. So now this is the first type of norm we have, the one norm. Okay.
Hello, sir.
Okay, sir.
Yeah, I think this would be a convenient point for us to end today's class.
Okay, sir.
Well, first of all, I want to appreciate the first and the last presenter for a clear thoughts in their presentation. Mr. Emmanuel, you didn't do a good job, and to that effect, I hope that you salvage yourself by next week, right? So that at least we have a good outing for the whole group. Yeah, so let me quickly take the attendance, then also take the score. So please be fast. Ordering D. Moses. Is Oderi Demos is present? Okay, absent. Akinrolabu. What? Who just
Amos is present, sir. My picks was not on properly, sir.
Don't waste my time. Akinrolabu.
Present, sir.
And then say Mbemena. Sorry. Is Mbemena present?
Yes, sir.
Yeah, so you should answer fast now. Ezekiel Toby. I think that guy is perpetually absent. Ele Bede Bankole.
Present, sir.
Yeah, please, if you also presented, let me know when I call your name.
No, I do not present.
Mbe Bu Samuel Chika.
Present, sir.
Abdulrahim Miriam.
Present,
Ola.
sir. Present, sir.
Okay, Agba.
Present.
Nadi, the big Nadi something.
Present, sir.
Osegwedwa Ebenezer.
Present, sir.
Yeah, you absent for 2 classes.
Sir, I was present, sir. It probably was network, sir.
Okay,
I
Shotan,
was present last week.
Cindy. Shotan Cindy.
Present, sir.
Akin Wande Oluwatobiloba.
Present, sir.
Who is Cindy?
Sir, I'm Cindy.
So who is Akin Wande?
I'm Akiwande.
How you people talking the same way? Oluwa Susi.
Present, sir.
Lawal Farouk.
Present, sir.
You're absent for last class.
Yes, sir. I was not feeling well, sir.
Oladipupo Jeremiah. Okay, absent. Musliuddin.
Yes, sir, present, sir. And I also presented, sir.
Oh, you're the first presenter?
Yes, sir. Yes, sir.
But you didn't attend the first 2 classes.
I attended last class, and I explained that I attended the first class also. I was one who sent the message to you on WhatsApp that I mistakenly signed attendance for the master students class last week.
Oh, you slept off.
No, like I sent a message, like I was in the class last week, and last week I complained that the first class also.
No. Hello. I'm not saying you were absent last week.
Okay, sir.
Upper week you were absent. That's when you slept off, right?
And I entered the master's class.
The first class you didn't show up.
The class of distribution class.
Yes. Abdulsalam Miriam.
Present, sir.
Okay. Fakorede.
Present, sir. Fakorede.
Oh, okay. Obaji. Sorry, Obaji.
Present.
Uluka Prince. One of the absent for all classes. Jebutu.
Present, Sam. I was the last presenter, sir.
Oh, great. Moshood Aliu. Perpetually absent. I think 3 people presented today.
Yes, sir.
Yes, sir.
I've only seen 2. Emmanuel what?
Sir.
Huh?
Mbemena. MBBEMENA.
You didn't say you presented now.
No, you already called my name, and then so after you asked me.
Okay. All right. Thank you for your time. So next week, the other fellow will take he will start. Then Mr. Emmanuel will try to redeem himself. Oladipupo will know. Who is Oladipupo? Let me see. Is that your surname? Oladipupo. Something like Present. Oh, okay. So why didn't you speak? Okay. Stop by treating. Okay, so I think I've treated all the issues online. Yeah, so you can go to what's the name? Is it still correct? Yeah, sorry, I ain't back. So I think you can go to this YouTube channel to watch what we have done today. So should they not send this thing to me? Or what's the name? The link. So you can, let's chat. All right, so you can copy that and watch the stuff on YouTube. Okay.
Sir,
Yes, please.
should I send a reminder message?
You what?
Like I sent a message last week to you or WhatsApp.
That's
regarding the class that said my name was in the attendance. So should I send another message to remind?
No, I've corrected that now.
Okay.
All right. So have you copied the link?
Yes, sir.
Yeah, please, you could check if the YouTube is working before I log out from here.
Yeah, the class was streaming.
Is what?
The class was streaming on YouTube. Like it is still streaming on YouTube.
It's what?
I mean, the class is streaming on YouTube.
Oh, okay.
It's working, sir.
Yes, I can hear you. Who said hello? All right, so have a nice weekend. Bye.